The afternoon of July 13th, 1943, 300 miles northwest of Cape Finisterre, Spain, Kapitänleutnant Werner Henke stood in the conning tower of U-515, scanning the empty Atlantic horizon through salt-crusted binoculars. His boat had been submerged for nearly 18 hours, batteries depleted to dangerous levels, the diesels needed to run, the crew needed to breathe air that didn't taste like sweat and machinery. He gave the order to surface. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The U-boat broke through the grey swells at 1400 hours. Henke's lookouts scrambled topside, their eyes adjusting to daylight after the red-lit darkness below. The sky appeared clear. No aircraft, no ships, just the endless rolling ocean that had been their hunting ground and their prison for 6 weeks. The diesel engines coughed to life, their familiar rumble a comfort to men who had lived with the constant threat of depth charges and the suffocating silence of evasion. 22 minutes later, a B-24 Liberator appeared from behind a cloud bank, diving directly toward them. Henke screamed for a crash dive. The lookouts tumbled through the hatch. Seawater cascaded into the conning tower as they sealed it. The vents opened with their characteristic hiss. U-515 tilted forward, desperate to reach the safety of depth, but the Liberator was already overhead. 4 depth charges fell in a perfect straddle pattern. The explosions lifted the submarine's stern, buckled hull plates, shattered gauges throughout the boat. In the suffocating darkness, as the emergency lighting flickered and men shouted damage reports, Werner Henke asked himself the same question that haunted every U-boat commander in the summer of 1943. How did they find us? The answer floated on the surface directly above them, transmitting acoustic data that Henke would never detect, never understand, and could never escape. A small cylinder, 3 feet long and 5 inches in diameter, bobbing in the Atlantic swell, listening to the sounds of his dying submarine with a hydrophone suspended 24 feet below the waves. The Germans called it the toes ring, the circle of death, but they didn't know what it actually was. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand how profoundly this weapon changed the Battle of the Atlantic, we must first understand what German submariners believed about their enemy's capabilities in 1943. The intelligence briefings at U-boat headquarters in Lorient, France, told a clear story. The Allies had developed sophisticated radar systems. These radar sets, mounted in aircraft, could detect a surfaced U-boat at ranges exceeding 20 miles. The British had also supposedly perfected infrared detection, capable of sensing the heat signature of a submarine's diesel exhaust against the cold Atlantic. These were the threats that dominated every tactical discussion, every training session, every nervous conversation in the officers' mess. The Germans knew about radar because they had experienced it directly. Their METOX receivers could detect radar emissions, giving them precious minutes of warning before an aircraft appeared. When the Allies switched to centimetric radar in early 1943, rendering METOX useless, German engineers scrambled to develop the Naxos detector. The technological race was visible, measurable, understood. Radar sent electromagnetic waves through the air. Detect those waves, and you could evade the aircraft. It was physics they could comprehend and counter. What they couldn't comprehend was how Allied aircraft found U-boats that had been submerged for hours, boats that hadn't transmitted on radio, hadn't shown any heat signature, hadn't broken the surface where radar could detect them. How did a patrol plane arrive? Precisely over a submarine that had been underwater since dawn, forcing it to remain submerged until its batteries died, and it had no choice but to surface directly into an ambush. German intelligence developed elaborate theories. Perhaps the British had perfected some form of magnetic detection, sensing the steel hull through the water itself. Perhaps they had deployed vast networks of underwater listening stations connected by cable to shore stations. Perhaps, as some desperate reports suggested, the Allies had recruited dolphins or trained seals to locate submarines. The explanations grew increasingly fantastic because the reality was too simple to imagine. A buoy, dropped from an aircraft, listening. The development of the sonobuoy represented a convergence of technologies so straightforward that its effectiveness seemed almost unfair. In May 1941, British physicist P.M.S. Blackett proposed the concept, an expendable acoustic sensor that aircraft could deploy over suspected submarine locations. The idea was elegant. Submarines made noise, water conducted sound efficiently, radio could transmit that acoustic information to an aircraft. Why did no one think of this sooner? The Americans did think of it, almost simultaneously. In June 1941, the Office of Scientific Research and Development contracted with RCA to develop a radio sonobuoy for deployment from surface ships. The initial design proved disappointing. The acoustic range was too limited. The electrical components were too fragile. The project was shelved. But the scientists at Columbia University's Underwater Sound Laboratory at Fort Trumbull, New London, Connecticut, refused to abandon the concept. They modified the design for air deployment. They simplified the electronics. They used materials that weren't critical to other war production. Paper tubes coated for waterproofing, flashlight batteries for power, vacuum tubes already in mass production. On March 7, 1942, the Navy blimp K-5 cruised over waters south of New London, monitoring two refurbished RCA sonobuoys as the submarine S-20 ran submerged below. The hydrophones detected the submarine's propeller noise at distances up to 3 nautical miles. The radio reception aboard the blimp remained clear at ranges up to 5 miles. The test lasted 3 hours. It proved the concept absolutely. Russell L. Mason, the civilian engineer aboard K-5 that afternoon, would spend the next 35 years refining the technology he had just witnessed revolutionize anti-submarine warfare. But in March 1942, all he knew was that he had just watched an aircraft detect a fully submerged submarine through acoustics alone, something that had never been accomplished in the history of naval warfare. By June 1942, the AN CRT-1 became the first operational sonobuoy. The first air-droppable version weighed 15 pounds and measured 3 feet long by 5 inches in diameter, a size that would become standardized as A size. The outer cylinder was constructed from 1/4-inch thick paper tube, hardly the material one would expect in a weapons system that would help win the Battle of the Atlantic. The coating kept it watertight for several hours, long enough to complete its mission. Inside, 5 vacuum tubes powered a half-watt radio transmitter tuned to one of 6 FM frequencies, each corresponding to a color: purple, orange, blue, red, yellow, green. The hydrophone, constructed of rugged nickel magnetostriction material, deployed to a depth of 24 feet on a weighted line. The system's genius lay in its simplicity. An aircraft operator could drop multiple sonobuoys in a pattern, then tune the AN/ARR3 receiver manually, using the color-coded tuning window to compare acoustic intensity from each buoy. By noting which buoy received the loudest signal, the operator could triangulate the submarine's approximate position. The acoustic signatures were distinctive enough that trained operators could differentiate between submarine propeller noise and ambient ocean sounds, between German diesels and Allied vessels, sometimes even between different U-boat classes based on propeller cavitation patterns. On July 25, 1942, a U.S. Army B-18 bomber dropped the first operational sonobuoy from an aircraft during an actual anti-submarine patrol. The technology transitioned from experimental to operational in less than 5 months, a development cycle that would be remarkable even today. By August, Colonel Dolan of the Sea Search Group operating out of Langley, Virginia, was expending sonobuoys in offshore operations against U-boats patrolling the American coast. The Germans noticed something was wrong almost immediately, but they couldn't identify what had changed. In the summer of 1942, U-boat captains began reporting inexplicable encounters. "We didn't know ourselves how it happened, sir," one commander told Admiral Dönitz during the mandatory debriefing after patrol. Suddenly, a Liberator came through a thick cloud layer straight at us and dropped his charges. They couldn't possibly have seen us. Another reported surfacing at night in heavy weather, conditions that should have made visual detection impossible and radar detection difficult. We were surfacing at normal speed, when suddenly we heard the noise of aircraft. They were directly overhead before we could crash dive. The pattern repeated across the Atlantic. U-boats approaching convoys at night found destroyers detached from the screen to intercept them before they could reach attack positions. Submarines that had maintained absolute radio silence found themselves under attack by aircraft that appeared to know their precise locations. Boats that crash-dived and evaded to new positions discovered aircraft waiting for them when they surfaced hours later, miles from their last known location. German naval intelligence analyzed every report, searching for the common factor. The conclusion seemed obvious. The Allies had deployed a new type of radar, possibly operating on wavelengths the German detectors couldn't sense. This explanation fit the evidence. It matched German understanding of Allied technological development. It suggested countermeasures that German engineers could develop. The alternative, that Allied aircraft were simply dropping listening devices into the ocean and waiting for submarines to make noise, seemed too primitive to consider. Too simple. Too effective. Admiral Karl Dönitz, the commander of the U-boat force, addressed the crisis in a May 1943 conference with Hitler. His analysis revealed both the sophistication of German tactical thinking and its fundamental blindness to the actual threat. The substantial increase of the enemy air force is the cause of the present crisis in submarine warfare, Dönitz explained. However, the submarine crisis would not have come about solely as a result of an increase of enemy aircraft. The determining factor is a new location device, evidently also used by surface vessels, by means of which planes are in a position to locate submarines. When the ceiling is low, visibility poor, or at night, they can carry out surprise attacks. Without this device, the planes would be unable to locate the submarines at night or in a heavy sea. Every word of this assessment was correct. Every conclusion was wrong. The new location device existed. Aircraft were using it with devastating effectiveness. But it wasn't the radar system Dönitz imagined. It was something far more insidious, a weapon that turned the submarine's own machinery against it, that exploited the fundamental requirement of underwater operations that propellers must turn, that diesels must run, that compressed air must flow through ballast tanks, and made every necessary sound a beacon for Allied aircraft. By December 1943, the United States Navy had ordered 59,700 AN CRT-1 as sonobuoys. These devices, manufactured with 6 radio frequency channels, were being distributed to anti-submarine squadrons across the Atlantic theatre. The production numbers alone should have alerted German intelligence to the scale of deployment. 59,000 units represented more than a technological experiment. It represented a systematic campaign to blanket the Atlantic with acoustic sensors that could detect submerged submarines at ranges German commanders believed impossible. But the Germans never captured an intact sonobuoy. They never recovered one from the ocean. They never examined its internal components or understood its operating principles. The paper casing, designed to be waterproof for only a few hours, ensured the devices sank after completing their mission. The electronics, damaged by seawater and pressure, became unrecognizable wreckage on the ocean floor. German naval intelligence possessed fragments of evidence, sonar contacts that appeared moments after aircraft passed overhead, acoustic conditions that seemed to predict attacks with uncanny accuracy, but they never assembled these fragments into recognition of the actual threat. The psychological impact on U-boat crews became measurable in ways that German naval command found increasingly difficult to ignore. In early 1943, before the sonobuoy reached widespread deployment, the average U-boat patrol lasted 65 days. Crews returned exhausted but confident, reporting successful attacks and narrow escapes that reinforced their sense of tactical superiority. By the summer of 1943, patrol durations had shortened to 47 days, not because boats were sinking more targets, but because commanders were aborting missions after experiencing the paranoia of being hunted by an enemy that seemed to possess supernatural knowledge of their positions. Korvettenkapitän Peter Kremer, commander of U-333, documented this psychological erosion in his war diary. "We crash dive at the sound of every aircraft engine, real or imagined. The men jump at shadows. Yesterday, the hydrophone operator reported propeller noises that turned out to be a school of fish. The day before, we dove because someone thought they heard aircraft, but it was just wind whistling through the periscope housing. We cannot continue this way. Every noise becomes a threat. Every moment submerged feels like being buried alive, and every moment on the surface feels like standing in an execution yard, waiting for the shot we won't hear until it's too late. The British, meanwhile, were conducting their own sonobuoy operations under the codename High T. In July 1942, RAF Coastal Command's No. 2 to 10 Squadron began operational use of sonobuoys from their short Sunderland flying boats. The British design philosophy differed slightly from the American approach, where American doctrine emphasized rapid deployment and triangulation using multiple buoys. British operators focused on extended monitoring of specific areas, using the Sunderland's long endurance to maintain acoustic surveillance for hours. Flight Lieutenant James Thompson flew one of those early high-T missions over the Bay of Biscay, the notorious stretch of water where U-boats transited between their bases in France and their patrol areas in the Atlantic. His after-action report, preserved in RAF archives, provides insight into the operational reality of sonobuoy warfare. Deployed 6 sonobuoys in a line across the suspected transit route at 0700 hours, Thompson wrote, maintained patrol altitude of 800 feet, monitoring all 6 frequencies in rotation. At 11:20 hours, buoy number 4, orange frequency, registered strong machinery noise consistent with diesel engines, altered course to investigate, maintained monitoring. At 11:47, visual contact with U-boat on surface, approximate bearing matching acoustic contact, attacked with depth charges, results assessed as probable kill. The clinical language concealed the revolution in anti-submarine warfare. Thompson had detected a submarine running submerged, tracked it acoustically, and positioned his aircraft for attack before the U-boat crew had any indication they were being hunted. The Germans would have attributed the attack to radar or visual sighting during a brief surface period. They would never have imagined that an aircraft had been listening to their engines through hydrophones suspended in the water miles away. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The technical specifications of the AN CRT-1 reveal why German detection proved so difficult. The hydrophone operated passively, emitting no signal that submarine sensors could detect. Unlike active sonar, which sent acoustic pulses through the water and listened for echoes, the sonobuoy simply listened to the ambient noise environment. A U-boat's hydrophone operators, trained to detect the active sonar pings from surface ships or the propeller noises of approaching vessels, had no way to sense a passive listening device floating on the surface above them. The radio transmitter operated on FM frequencies between 36 and 50 MHz, well outside the range of German radio direction finding equipment designed to intercept naval communications in the much lower frequency bands. Even if a U-boat's radio operator happened to tune across one of the sonobuoy frequencies, they would hear only the modulated audio signal representing underwater sounds, which would be meaningless without the context of knowing what they were hearing. The operational doctrine that evolved around sonobuoy deployment exploited German tactical patterns with ruthless efficiency. U-boat commanders, trained in a warfare philosophy that emphasized aggressive action and decisive engagement, followed predictable behaviors when under threat. When detected by radar, they crash-dived to evade the immediate attack. When harassed by aircraft, they moved to new patrol areas under the cover of darkness. When low on battery power, they surfaced in locations they calculated to be beyond aircraft range. Allied anti-submarine forces learned to anticipate these patterns. An aircraft detecting a U-boat with radar would mark the dive location, deploy a pattern of sonobuoys around the area, then wait. The submarine, believing it had successfully evaded, would eventually need to surface. The moment its diesel started, the moment its propellers began turning, the sonobuoys registered the acoustic signature. The aircraft, which had appeared to leave the area, would return with devastating precision. Oberleutnant zur See Heinrich Müller experienced this tactic in September 1943 while commanding U-737. His patrol report, recovered from German archives after the war, documents an encounter that perfectly illustrates the psychological warfare dimension of sonobuoy operations. At 03:15 hours, radar detector indicated aircraft approach, Müller wrote. Executed emergency dive to 90 meters. Maintained silent running for 2 hours. Hydrophone reported no surface vessels in area. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. At 05:30 hours, with batteries at 32% capacity, surfaced to run diesels. Within 4 minutes of surfacing, aircraft appeared from cloud cover and attacked. Sustained minor damage from near-miss depth charge. Crash dived successfully. Cannot explain how aircraft located us. Radar detector gave no warning of approach. Hydrophone detected no surface vessels that could have marked our position. Weather conditions poor, with low clouds and rain squalls making visual detection nearly impossible. Crew morale severely affected, men asking questions I cannot answer. The questions Müller couldn't answer would haunt U-boat operations for the remainder of the war. How did aircraft know exactly where to search? How did they arrive so quickly after surfacing? How did they maintain contact even when the submarine evaded to new positions? The psychological burden of fighting an enemy who seemed to possess inexplicable knowledge of submarine locations transformed the nature of U-boat warfare. In 1942, German submariners called themselves Grey Wolves, hunters who struck from the depths with deadly precision. By late 1943, they had become prey, constantly hunted, always vulnerable, never safe, even in the vast emptiness of the Atlantic. The change wasn't just tactical, it was existential. The acoustic signature of a Type 7C U-boat, the most common German submarine design, became as distinctive to trained Allied operators as a fingerprint. The diesels produced a characteristic low-frequency rumble between 20 and 100 Hz. The electric motors, used for submerged operations, generated higher frequency noise from brush contact and armature rotation. Most distinctively, the propellers created cavitation bubbles, tiny voids in the water caused by the rapidly spinning blades, which collapsed with sharp acoustic pops that carried for miles underwater. American and British acoustic analysts developed detailed classification systems for these sounds. Training programs at bases in Norfolk, Virginia, and Londonderry, Northern Ireland, taught operators to distinguish between different submarine classes, to identify whether a boat was running on diesel or electric power, to estimate speed and depth based on propeller rotation rates and machinery noise levels. The level of detail became extraordinary. Some experienced operators claimed they could identify individual U-boats by subtle variations in their fur. Acoustic signatures, like recognizing a person by their voice. The Germans remained completely unaware of this acoustic intelligence capability. Their own hydrophone technology, while sophisticated, focused on detecting other vessels, not on understanding how their own submarines sounded to enemy sensors. German acoustic research concentrated on developing acoustic torpedoes that homed on the propeller noise of Allied ships. The concept that the Allies might be using similar principles to hunt submarines apparently never gained traction in German naval research programs. This blindness persisted despite mounting evidence that something fundamental had changed in Allied anti-submarine capabilities. In May 1943, Admiral Dönitz withdrew U-boats from the North Atlantic convoy routes after losing 41 submarines in a single month. The losses were unsustainable. The tactical situation had reversed completely. In the early war years, U-boats attacked convoys. Now, convoys hunted U-boats. Dönitz attributed the crisis to Allied air power, to improved radar, to the closing of the mid-Atlantic air gap where U-boats had once operated beyond the range of land-based aircraft. All these factors contributed to German losses, but the sonobuoy represented something more insidious, a weapon that made the ocean itself hostile territory, that transformed every square mile of Atlantic water into a potential listening post that gave aircraft the ability to detect submarines in conditions where radar and visual observation failed completely. The scale of sonobuoy deployment in the final 2 years of the war reached levels that would have shocked German intelligence had they known. Between October 1942 and May 1945, Allied forces dropped approximately 150,000 sonobuoys into the Atlantic. Some were deployed in systematic patterns, creating acoustic barriers across known U-boat transit routes. Others were dropped, opportunistically, marking areas where submarines had been detected or were suspected to operate. Still others were used in hunter-killer operations, where surface ships and aircraft coordinated to trap U-boats in progressively smaller areas, using sonobuoys to maintain contact even when the submarine dove to extreme depths. The tactical employment of sonobuoys evolved throughout 1944 and 1945 into increasingly sophisticated patterns that German commanders never fully understood. The barrier pattern, developed by US Navy patrol squadrons operating from Iceland and Newfoundland, involved deploying lines of sonobuoys across known U-boat transit routes. Aircraft would lay a pattern of 15 to 20 buoys in a line spanning 20 to 30 miles, creating an acoustic fence that submarines could not cross without detection. Once a sonobuoy registered contact, additional aircraft would converge on the area, deploying more buoys to track the submarine's movements and maintain contact until surface ships arrived to prosecute the attack. Kapitänleutnant Hans-Georg Hess, commanding U-995, encountered one of these barriers in February 1944 while transiting from Norway to patrol areas southwest of Ireland. His experience, documented in both his patrol report and post-war interrogation, illustrates how sonobuoy operations appeared from the German perspective. "We were proceeding submerged at 4 knots, running on electric motors to minimize acoustic signature as ordered by command," Hess reported. Depth 120 meters, no radar emissions detected, no surface contacts on hydrophone. Sea state calm, excellent conditions for remaining undetected. At 1400 hours, hydrophone operator reported distant aircraft sounds, bearing indeterminate. We reduced speed to 2 knots and maintained course. At 1430 hours, first depth charges, approximate range 2,000 meters. We altered, course 90 degrees. More depth charges at 1500 hours, closer this time. We increased to 6 knots, altered course again. Aircraft seemed to anticipate our movements. Charges fell consistently within 500 meters of our position, despite our evasive maneuvers and despite maintaining continuous submerged operations. We cannot explain this. It is as if the enemy can see through the ocean itself. What Hess couldn't see were the 8 sonobuoys deployed in a line across his transit route, their hydrophones detecting the electric motors and propeller noise of U-995 as it attempted to evade. What he didn't know was that each course change, each speed adjustment, was registered by the acoustic sensors and relayed to 3 circling aircraft that took turns attacking, while the others monitored the sonobuoy frequencies. The submarine was never beyond observation. Every sound it made, every mechanical necessity of underwater operations, betrayed its position to enemies Hess believed were guessing his location through some inexplicable combination of radar and luck. The cumulative psychological effect on U-boat crews manifested in ways that German naval medicine struggled to address. By late 1944, the average patrol report included references to crew anxiety, sleep disturbances, and what German psychiatrists began documenting as Horchfurcht, listening fear, a condition where hydrophone operators became convinced they could hear Allied detection devices that didn't actually exist. Men reported hearing mechanical clicks, electronic hums, rhythmic patterns in ocean noise that they interpreted as enemy sensors tracking their boat. The paranoia had a basis in reality. Something was hunting them with supernatural precision. But the specific mechanisms they imagined, underwater robot sentinels, cable networks linking shore stations, magnetic sensors detecting steel hulls from impossible distances, bore little resemblance to the simple paper cylinders bobbing on the surface above them. The German response to unexplained aircraft attacks concentrated resources on countermeasures that addressed the wrong threat. Engineers developed the Naxos radar detector to replace the obsolete Metox system. They designed coating materials intended to absorb radar waves and reduce the submarine's radar cross-section. They experimented with infrared-absorbing paints after becoming convinced the British had perfected infrared detection. Millions of Reichsmarks, thousands of man-hours, entire research programs addressed a threat model that was partially correct but fundamentally incomplete. The one German countermeasure that might have detected sonobuoys never received sufficient development priority. In 1943, German engineers proposed equipping U-boats with receivers capable of scanning the FM radio spectrum used by Allied aircraft communications. The technology existed. The Germans had excellent radio direction-finding equipment, but the project received low priority because German intelligence believed Allied aircraft were using radar, not radio-transmitted acoustic data, to locate submarines. The receivers that could have detected sonobuoy transmissions remained prototypes, while U-boats continued dying from attacks they couldn't understand. The operational records preserved in Allied archives reveal the devastating effectiveness of coordinated sonobuoy operations. In March 1944, aircraft from escort carrier USS Guadalcanal, operating southwest of the Azores, deployed sonobuoys to locate U-544 after the submarine had evaded an initial depth charge attack. The aircraft maintained acoustic contact for 7 hours, while the destroyer escorts USS Pope, Flaherty, Pillsbury, and Chatelaine converged on the area. The surface ships, guided by continuous position updates from the aircraft monitoring sonobuoy frequencies, pursued U-544 through multiple evasion attempts. The submarine finally surfaced after 23 hours of continuous pursuit, its batteries exhausted, its crew unable to continue. The capture of U-544, along with its codebooks and Enigma machine, represented one of the intelligence coups of the Battle of the Atlantic. The operation succeeded because sonobuoys provided continuous tracking that prevented the submarine from escaping. Kapitänleutnant Harold Lange, the commander of U-544, described his experience during post-capture interrogation. "We could not understand how the destroyers maintained contact," Lange explained. "We changed depth. We changed course every 30 minutes. We ran silent. We released bold decoys, the metal foil strips that should have confused their sonar. Nothing worked. They knew where we were at every moment. Some of my officers believed the Allies had developed acoustic torpedoes that tracked submarines. Others thought the Americans had placed detection devices on the seabed. I had no explanation. I still have no explanation. It was like being hunted by ghosts who could see through steel and water." The irony of Lange's statement lies in its accuracy. He was being hunted by devices that effectively saw through water, not with light or radar or magnetic sensors, but with the oldest form of remote sensing known to humanity: sound. The sophistication lay not in exotic physics, but in the systematic application of basic acoustic principles, the recognition that submarines must make noise to operate, and that water conducts sound efficiently enough to detect that noise at tactically useful ranges. By early 1945, sonobuoy technology had advanced beyond the simple omnidirectional hydrophones of the AN-CRT-1. Development of the AN-CRT-4 directional sonobuoy began in February 1943, though the system didn't reach operational testing until early 1945, too late to affect the European War. This larger, more sophisticated device measured 6¼ inches in diameter and 52½ inches in length, weighing 30 pounds. It featured a rotating directional hydrophone turned at 3 to 5 rotations per minute by a gravity motor using a 500-foot-long fishing line. The directional capability would have allowed single buoys to provide bearing information without requiring triangulation from multiple sensors. But the war in Europe ended before the AN-CRT-4 could prove its operational value. The Germans never learned about sonobuoys, not during the war, not through captured equipment, not from interrogation of Allied personnel. The security surrounding the technology remained intact until well after Germany's surrender in May 1945. When German naval officers were finally briefed on sonobuoy capabilities during post-war technical exchanges, their reactions ranged from disbelief to resignation. The simplicity of the concept, the elegance of the execution, the effectiveness of the deployment, all combined to illustrate how profoundly they had misunderstood the nature of the threat they faced. Admiral Dönitz, in his post-war memoirs, reflected on the technological race that decided the Battle of the Atlantic. "We knew the Allies had radar," he wrote. "We developed detectors and countermeasures. We knew they had improved sonar on their escort vessels. We developed tactics to evade it. We knew they had broken some of our codes. We implemented new encryption procedures, but we never knew about the listening devices they dropped from aircraft. We couldn't defend against a threat we didn't know existed. Perhaps that is the most bitter lesson of all. We were defeated not by superior force alone, but by superior knowledge of our ignorance." The final statistics of the Battle of the Atlantic reveal the magnitude of the German failure to understand Allied capabilities. Between 1939 and 1945, Germany commissioned 1,154 U-boats. 783 were lost in combat, a casualty rate of 68%. Approximately 30,000 German submariners died, 3/4 of the 40,000-man submarine force. These losses occurred despite German submarines sinking approximately 3,000 Allied merchant ships, totaling 14.5 million gross tons, and 175 Allied warships. The exchange rate favored the Allies overwhelmingly, not because German submarines weren't lethal weapons, but because Allied detection and tracking capabilities rendered them vulnerable to a degree that German naval command never fully grasped. The sonobuoy represented only one component of the Allied anti-submarine warfare system. Improved radar, high-frequency direction finding, ultra-intelligence from decrypted German communications, escort carriers providing air cover, very long-range patrol aircraft closing the mid-Atlantic gap, all contributed to Allied victory. But the sonobuoy possessed unique characteristics that made it particularly devastating. It worked when radar failed in bad weather. It detected submarines that maintained radio silence and thus provided no signals for direction finding. It tracked boats that had dove too deep for magnetic anomaly detectors. It turned every Allied aircraft into a potential submarine hunter, even in sea states and weather conditions that rendered visual observation impossible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The legacy of World War II sonobuoy development extended far beyond the immediate tactical applications in the Atlantic. The AN, CRT-1 and its successors established the fundamental principles of airborne anti-submarine warfare that remained relevant through the Cold War and into the 21st century. Modern sonobuoys, vastly more sophisticated than their World War II predecessors, continue to serve as primary sensors for maritime patrol aircraft and anti-submarine helicopters. The basic concept, a disposable acoustic sensor deployed from aircraft and transmitting data via radio link, proved so effective that subsequent decades of technological advancement merely refined the execution rather than replacing the fundamental approach. The German submariners who survived the war carried with them the memory of being hunted by an enemy whose capabilities they never fully understood. In veteran reunions, in oral histories, in the memoirs published decades after the conflict ended, former U-boat crews described the paranoia of submerged operations in 1944 and 45, the conviction that Allied forces possessed some form of supernatural knowledge, the helplessness of being attacked by aircraft that appeared from nowhere and departed after dropping depth charges with impossible accuracy. They were correct. The Allies did possess knowledge that seemed supernatural from the German perspective. But it wasn't supernatural. It was acoustic. It was systematic. It was effective. And it remained secret long enough to help win the Battle of the Atlantic and ensure that the sea lanes between America and Britain remained open, allowing the build-up of forces that would eventually liberate Europe. The story of the sonobuoy and German ignorance of its existence stands as a testament to the decisive importance of technological surprise in warfare. Not the most advanced technology, not the most powerful weapons, but the unexpected application of proven principles in ways that enemy intelligence cannot anticipate or counter. The Germans never knew that paper tubes filled with batteries and vacuum tubes, dropped from aircraft and floating on the Atlantic swells, were listening to every sound their submarines made and transmitting that information to enemies circling overhead. That ignorance cost them the Atlantic, their submarine force, and ultimately their war. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.